This topic will address performing basic operations on 2-dimensional and 3-dimensional vectors. But before we start operating on vectors, let's do a quick refresher or a primer on what is a vector quantity. So if we go back to our first physics class where we first talked about vectors, the classic definition that was provided to us is that a vector was a quantity that had both magnitude and direction. So if we think of, in contrast to this, scalar quantities like temperature, it has a magnitude but no direction. But when we talk about a vector quantity, let's say velocity, we'll have a magnitude and a direction to it. So we might be going 30 miles per hour north or 25 miles per hour east. We need both of those quantities to fully describe our velocity vector. Now we'll begin more simply with 2-dimensional vectors, and we're going to have two ways of representing these. We're going to do our operations in the Cartesian form, but sometimes we're going to report our final answer, or we're going to start with a diagram where we're given our vector in a polar form. Again, both of these are going to be useful. The polar form is a little bit more intuitive for us to understand the magnitude and the heading or the direction, but the Cartesian form is much more convenient for all of the operations we're going to be performing in this section. So if we have a vector with two representations, this is the same vector here. We can represent it as, in Cartesian form, 5i plus 3j newtons, where we're going to talk about what is this I and this j, or we can represent it as 5.83 at an angle of 31 degrees newtons. So again, both of these we're going to see have the same magnitude and the same direction. This is just two different ways to write it, two different ways to represent it. So when we're in the Cartesian form, we're going to be able to do the coming operations on our vectors. And we're going to talk about adding vectors, subtracting vectors, the dot product or dotting our vectors, and then the cross product or crossing our vectors. There's other operations you'll see in a linear algebra or a matrices class, but these are the four that we're going to be using for this class. Now this is what we can do with two vectors together. What can we do if we have a vector quantity and a scalar quantity? Well, those things we can multiply a vector by a scalar. We can also divide a vector by a scalar. In linear algebra terms, we are not able to add a vector and a scalar together because their dimensions don't agree. We cannot dot or cross a vector and a scalar because, again, the dimensions are not in agreement here. And when we get to those topics, we'll see why a scalar quantity is not compatible with a vector quantity except for simple multiplication or division. Now, the vector quantities we're going to deal with most in this course are going to be force and distance. So these quantities we can represent in this Cartesian or polar form. So we'll begin with the simplest of the ways that we can operate on vectors is we can add our vectors together. And again, we're going to stick with 2 dimensions for now, and then later we're going to address what happens when we go to 3 dimensions, although the process is going to be largely the same. So we can take 2 or more vectors and we can add them together. And what happens when we add multiple vectors together is we're going to get something called the resultant vector. So in math representation here, if I have the sum of F equals R, this means I'm summing together multiple forces or multiple vectors, and that equals R, the resultant vector. And what this does is lets us really simplify a system, because we can say that, for example, we can add all of these force vectors together and get the resultant. And really what we're finding is what's the net result of having all of these force vectors act simultaneously on our object. So instead of writing 2 or 3 or 4 force vectors, we could replace all of those vectors with a single R vector. And as far as the object is concerned, that one resultant vector is going to have the same effect as those multiple force vectors do. Now, before we proceed with adding our 2 vectors together, what we're going to want to do first is make sure that all the vectors that we want to add together are represented in what we call the Cartesian component form. And what the Cartesian component form does, as we saw in the previous slide, is it's going to break down our vector into what we call the I and the j components, or the I and the j directions. So it tells us how much of our vector lies along this I or X axis and how much of it lies along the J or the Y axis. And we'll see that we can extend that in 3 dimensions as well. Now, what we can't do is if we're in the polar form, we can't easily add our vectors together. So we can't have 3 newtons at 20 degrees plus 8 newtons at 45 degrees and simply add their degrees together, add their magnitudes together, and get an answer. It's not compatible that way. However, if we first convert each of those into their component form, what we will be able to do is add their like components in the I terms and the J terms, and then once they're added together, we're going to be able to go backwards and find the resultant vector in polar form if we wish, with its magnitude and its direction. So sometimes this Cartesian form is just kind of an intermediate step in order to add our polar notated vectors together and then get something in the polar form. But we're going to see as we get further along in this course, simply leaving it in the Cartesian form is going to be fine for our purposes. So how do we put our vectors into this Cartesian component form? We're going to do something called decomposing our vector. So again, instead of simply expressing it as a magnitude and direction, that polar form, we're going to say how much of it lies along specific axes. Typically, the x-axis and the y-axis when we're in a Cartesian system, which is typically what we're going to be operating in. So let's see here, if we have this vector f that points from A to B, so we see that the arrow is pointing in the B direction, so we say it starts at A, it points towards B. Now, we might be given its magnitude and its direction. We'll see in our examples what this is going to look like, but its direction is typically going to be measured counterclockwise from the x-axis and then has, again, some magnitude. When we decompose this, we want to see how much of it lies along our Cartesian axes. So what we can do is I can see how much of this is along the x direction. I'll call this f sub x. And I can see how much of this lies along the y direction. And I'll call that f sub y. Now, what have I done here? Basically, again, I'm just expressing my vector in a different way. If we think of a vector like a sequence of directions, this would be saying, okay, how do I go from point A to point B? Well, one way I could go is I could simply take the straight line that points from A to B. That's what f is representing. And I just need to know what my heading or what my direction is to go from A to B, and then how far along that I need to go. And that's what f is representing. Alternatively, if again my instructions are how do I get from A to B, I could say, all right, go along the x-axis by an amount fx. Then when you get to the end of that, go along the y-axis by an amount fy. And the end result of that is also I have gone from A to B. I've just kind of taken a different route to get there. I've taken a different representation of that force vector f, going directly knowing the heading or the direction, or going along specifically the x-axis and the y-axis. So what I can do is I can write my vector f as fx I hat plus fy j hat. And take a notice here of the notation I'm going to be using on the slides is that a vector is always going to be denoted by boldface on the slides. When I am writing it by hand, I'm going to be putting a line over my vector to represent vector notation. If something does not have a line or boldface, then we're going to say it's a scalar quantity. And then that hat, like over the I and the J, is also indicating a vector quantity, although specifically a unit vector, which we'll talk about in a little bit. So vector f equals some magnitude fx along the I hat or the x direction plus some scalar magnitude fy along the j hat or the y direction. So that's the big picture of how we decompose these vectors. What's the method that we are going to typically use? Well, first of all, whenever we're dealing with vector quantities, we need to know what coordinate system we are working in. As we saw on the previous slide, typically our coordinate system will be x positive to the right, y positive up if we're in 2 dimensions. That is not universally the case, and we never want to assume that. So always on every diagram we draw that's going to involve I, j, k components, we need to establish and draw explicitly what the coordinate system is. Then all the vectors we want to do operations with, whether it's adding like we're talking about now, or dotting or crossing, which we'll get to later, all the vectors we're going to be dealing with, we want to express in this Cartesian component form, the I and the j, and in 3 dimensions, k form. So once all of our vectors are in this Cartesian component form, and we want to add them together, now the process is going to be fairly simple. We can take the I component of all of our vectors that we want to add and add those I components together, and that's going to be the I component of the resultant. Then we can do the same thing with the y components of the vectors we're adding together, add all of those y magnitudes or coefficients together, and that's going to be the y component of the resultant vector. So what we have at this point, once we add those like components, is we have our resultant in Cartesian component form. It has an I and a j component. Now possibly we want to now express that resultant in a little bit more intuitive form, the polar form. So what we can do is now go backwards, and we're going to take this Cartesian form and put it back into the polar expression, the magnitude and the direction. All right, so what we want to be careful anytime we're dealing with putting things into vector form is we pay attention to our coordinate system. Like I said, typically x is positive right, y is positive up, but however we draw or establish our coordinate system, that is what we need to stick to in how we're defining positive directions of our vectors. Again, one more note on the notation. Scalars are going to just be a plain face, whether it's on paper or it's on the slides. Vectors are going to be typically bold on the slides, but have that overline when we write it out. And unit vectors have that hat over it. And we're also going to see that vectors can be freely moved along what we call their line of action. And this is going to come up a little bit later, but we want to just be aware of that now. But later I'll talk more about what is this line of action.